Hey guys, a short one here, but a tricky one for sure. We're going to talk about another condition that has to be satisfied in order for us to say that equilibrium um, has been achieved. Okay, so this gets into an element that I didn't touch on as much as I wish I had in our regular look at dynamics, um, but it's something that'll pop up on the next page, so it works okay. So what else does equilibrium mean? Well, for us, so far, we've said that for a system to be considered in equilibrium, we would say, well, what that means is that the net force is zero. All forces add up to zero. Now, um, we made an assumption, or we've been making an assumption, whether or not you know it, that forces all act on a special place on an object, right? And it's kind of like saying, all right, um, a question's about an elephant, but we don't bother drawing. Want to see an elephant? I'll draw you an elephant. Huh? Ears? Oh boy, that just got bad. Trunk. That's not bad actually. Other foot. Ooh boy. Tusks. There's an elephant. Yikes. Um, Tail. When we say, all right, something pushes on an elephant, what we're not considering is the fact that pushing, let's say we push here as opposed to pushing here. Well, different things can happen. All right, we've really been sort of assuming that we're pushing right here, where we call the object's center of mass. All right, I know it's sad to see this guy go here, but we're going to have to get rid of him. And the reason we say that, I'll make something quite a bit simpler, is imagine we have a meter stick, right? If we push with a force here at the center of mass, what we end up with is what we call translational motion. The object, we can push it over to there, okay? But if we don't push at the center of mass, and say we push up here, what we can get is, even though an object might not move translationally, this thing might not actually move this way, what we might get is the object rotates. All right? You can imagine that our meter stick might just rotate. Well, I'll draw it right here. It might just rotate about a certain axis. You can imagine that happening, right? We lay a meter stick on the table, we push towards the end, and the thing doesn't necessarily move across the table, but it still rotates. Right? If forces don't act on center of mass, rotation can certainly happen. And the tendency of a force to make something rotate is called torque. I don't know how many people listen too carefully to ads for pickup trucks or anything like that, but they'll always talk about a couple of things: horsepower and torque. Right? Horsepower is great. It means we can do a lot of work or expend a lot of energy quickly. It also, and well, the torque part means that the engine has a ton of ability to make something turn. And what you want to turn, well, is the engine really, but the drive shaft, which connects, well, here's the truck, right? Engine in here, engine's connected to flywheel somewhere back here, and flywheel is connected to drive shaft, which is connected to the differential in the back, which makes some gearing that makes the tire spin. But this drive shaft, we have to be able to turn that even at low speeds, right? So that rotational capability of an engine is a big selling factor for things like a pickup truck. All right, so torque is the ability to twist stuff or make stuff rotate. Let's look at a few situations and see if we can use some intuition to figure out in which cases forces can cause a lot or a little torque. So this is what we call, I don't know what you want to call it, but this is like a hinge, right? A hinge here. And we have this, imagine this is just like a bar. And this could be a top view, whatever you want. Imagine it like a door even. We're looking like a top view of a door. So the question is, which force, or really, at what point of application of the force, either here or here, which one of those is going to give us the most ability to create rotation? Or really, translation, which one causes the most torque? Well, it's this one. All right, hence, we put door handles all the way out here as opposed to putting door handles here, right? It's much easier to produce a rotation of the door about this axis if we apply the force far away from the axis. Make sense? Okay. Well, what about a case like this? Which force causes the most torque? Which one allows us the greatest capability to make this object rotate? Hopefully this one's kind of a no-brainer. Yeah, the more force we apply, the more ability we have to make things rotate. Okay? Now, what about this one? Okay? Which of the forces, all the same magnitude force, all the same strength of the force, which one is going to allow the greatest ability or afford us the greatest ability to make this object rotate? Well, it's this one. All right, this one won't make any rotation. Yeah, see that? It's all jacked up down here. Here it's okay. Here it's pretty good. Here it's right on. Down here, oh, now it's all right. Sorry, folks. This one down here will not make the object, make that bar rotate at all. We're just pulling on the bar. We'll get no rotation at all. Here we could get some rotation, but this one, if we push perpendicular to the to that bar, that's going to afford us the most ability to make that object rotate. It's going to produce the most torque. Okay, so this identifies three different factors. It should identify three different factors that affect how much torque a force causes. One of them is how far away from the what we call axis of rotation. How far away from the axis of rotation the force is applied. That's one factor that affects how much torque a force produces. The second, is the amount of force that we apply. And third, well, is the direction of the force. And we'll get more specific on the next page, but just want to make sure that we understand why we're asking or looking at each of these situations. Okay? Okay. Oh my. I thought for sure, yeah. Why does it all pop up at once? Good. Now, so apparently, yes, torque depends on the following factors. Well, the stuff we just talked about. So the question here is, let's say that we have, the situation we looked at in the last slide. We have this force F applied to this object here. And the question is, well, really, how can we express how much torque that force produces? Well, one of the big deals is right off the bat, the question is how much of that force is responsible for producing torque? Well, it's really this component right here. That component of force F, and force F has this component also. I'm going to call this one F perpendicular. I'm going to call this one F parallel. That'll help us. It's going to help us a lot, believe me. So F perpendicular produces torque. Torque, I'll call that the torque producer, F parallel, right? The part of the, F perpendicular, right? F parallel here doesn't produce any torque. It's just like us, pulling, well, it is us pulling this way on the door. It's not going to open the door, right? If we imagine this is a top view of a door again. So F perpendicular is the part of F, the component of F that produces torque. Woo. Now, by definition, torque is called a cross product. Now, we use this tau. Come on. Tau. It's the stupid smart word. Yeah, to mean torque. Okay? It's a kind of a capital T. If you want to use capital T, fine. And what we say, the words, we literally, physicists will say that torque is called R cross F. It's not R times F. It's called a a vector operation, a cross product is called a vector operation, a thing you can do with vectors, right? We can add vectors, right? You can take the cross product of two vectors. You can take what's called the dot product. I bet you've heard of dot product in math. We'll talk about dot products at some point. But yeah, this is called a cross product. So we need two vectors, right? We need this vector r, and here's vector r. And I think I define it. Yeah, not r times f, r cross f. Yeah, and now by definition, you know, if you want to take the cross product of any two vectors, right? Let's say we want to take the cross product of vectors a and b. Well, by definition, what you do is you take the magnitude of a, you take the magnitude of a, you take the magnitude of b, and you multiply them by the sine of the angle in between them. Okay, so notice there's our angle theta. And what I'm doing is I'm really assuming that I've taken vector r and sort of moved it over here, and then yeah, that gives us that angle between the two vectors. Okay? Now, come on. So F, sure, is force, measured in newtons, right? R. You got to know this. This is the definition of R, and it's super important. R, by definition, is a vector that starts at what we call the axis of rotation. Come on. What's the dealio? At the axis of rotation, and it goes to the what we call the point of action or point of application of the force, right? So here's the axis of rotation. I'll sometimes call it an AOR. And here's the point of application, where the force actually acts. Okay, that's what vector R is. And again, yeah, so notice what's great about this, I mean, why it works, why torque is a cross product, is because here's by definition how you do a cross product. Well, we're not doing general vectors A and B, we're doing vectors R and F. Right? So if torque is R cross F, then torque by definition is magnitude of R, magnitude of F, and sine of the angle in between them. Now notice, what is F sine theta? Well, F sine theta gets us, this is really R times F perpendicular, not FT. F perpendicular. You get that? That's a perpendicular thing. This board is driving me nuts. You got to write without looking. So this is torque equals R times F perpendicular. Duh. Whatever. All right, so what this does for us is it finds the component of the force that's perpendicular to R. Okay? So we're going to look, you know, one way to approach these problems, and we'll solve some problems, is just to sort of blindly do this. Find R, find F, find the angle between them, multiply them together. The other way that might be more valuable for a lot of us is to really try to do this, right? Make sure we're actually calculating the component of F that's perpendicular to R, right? Because that's the only component that produces the torque, produces the rotational action, okay? Yeah, so clearly here, you know, when is torque going to be the most? Well, when theta is, well, the biggest that a sine function can be is 1, and that happens when theta is 90, right? Or, of course, it happens, like we said in the first page, when the force is applied perpendicular to the thing we're trying to rotate, right? Forces can't produce any torque at all. Sine functions can be 0 when, excuse me, when the angle is 0. Right, and that's that case where F acts right along the axis like that. That's going to produce no torque at all. Fair enough? Okay. Simple sort of problem here. Let's calculate torque in a few cases. 10 kilogram object, blah, blah, blah. Leg lifts. Okay, so calculate torque. Well, let's call this position 1, 2, 3, 4. So at position 1, well, torque is R F sine theta, or R F perpendicular. Well, let's see. The force here, the force we have to, I guess the question is, yeah, the force that we have to apply. Well, I guess what they're really asking is how much, right, how much torque does the weight force produce? Right, so in this case, in case 1, how much torque, how much rotation does a force like that produce? Well, here's vector R, R1, all right? And here's really F1. Well, the question is how much of this force F is perpendicular to that vector R? None of it, right? And the reason is because the angle between them is 0. So in this case, we get nothing. Okay? Here's our vector R, right? There's R. Now the angle between these is, just like they tell you, 30 degrees. Or what you could really do is say, I'm going to make this a little bigger. I'm going to make this weight force look like that. And what we could say is the weight force has a component. Well, here's what we call weight parallel to R, and here's what we call weight perpendicular to R. And that's the component of the weight force that applies the torque or creates the torque. And yes, if this is 30, then that's going to be W sine 30 because it's opposite this angle 30. So yes, we just do for 2, torque is R, 40 centimeters, 0.4 meters, times F. Let's see. Well, F is mg. So 10 kilograms times 9.8 meters per second times the sine of 30. Torque is, let's see, this is 5, that's 49 times 0.4, 19.6. Well, 19.6 what? Well, meters, newtons. Well, we call that a Newton meter. Okay? Good there? Okay. In case 3, I'm just going to sort of follow what we were doing before. The only thing that's going to change now is, well, 0.4 meters times, watch this, the weight is just 98 newtons times the sine of 60. Torque is, we'll call it 34 Newton meters. And then in case 4, just so we're sure, right? Here's R. Here's F. 90 is the angle between them. So all we do here is torque equals 0.4 times 98 newtons times the sine of 90 times 1, right? 98 times 0.4, 39.2. Okay, so we see here, as the angle between R and F gets bigger, right? Angle gets bigger as we go this way, we produce more torque. Right? All the way from no torque to a little more to the max. Okay? Okay, now, typical problems. All right, I'm just going to throw this in here. you know, the big deal is if we want to look at general solution methods. I mean, just like every problem that we ever do, because this does involve, this is a forces, still a forces problem. You know, start with a free body diagram. Okay, you will still use net force statements. Now, what we're going to do, you know, forces can cause rotation. What we're going to do is actually look at situations where things don't rotate, right? And they're going to, so we say that things are in rotational and translational equilibrium. So we're looking at forces that could cause rotation, you know, but we're going to look at situations where there are forces that could cause rotation, but they don't because they're the right size and applied in the right place. All right, so for things to really be in equilibrium, right, we have to say this is true, and we have to say this is true. All right, those are the two big, these are the main, what do you call them, equilibrium conditions. All right, net force has to be 0, and net torque has to be 0. This is for, I'll say, provides translational equilibrium, and this provides rotational equilibrium. Okay? Now this says we can choose axes of rotation carefully. You'll see that in a minute. So yeah, in the hardest kind of problem, in typical problems, you'll end up doing this and this, and then sometimes coming back to a different net force statement. I don't know how much of this will make sense until we do a problem, but you know, not a bad little reference. Okay. Oh yeah. Well, I guess I just said that. Right here are the two big deals. All right. For something to be in equilibrium, those are the two things that have to be true. And the neat thing, we'll show you this. This will actually be part of your homework. The neat thing is it has to work around every single axis that you could choose, and it will. All right, I'll show you that. So here's a typical problem. We got a 5-meter long rod. There's its mass. It's balanced, which means it's in static equilibrium on a fulcrum by applying an unknown force at its left end. We got to find the normal force that the fulcrum exerts on the rod, and we have to find F. All right, yeah, here's a big one, big one, big one. All right. We are going to assume, and it does, that gravitational forces act on objects' centers of masses. Okay? So you can imagine that there is a force here that we could call mg, the weight of, what do we call this? The rod. All right? Well, that would typically make this object want to rotate around that axis. Well, to keep it from doing that, we apply a force here on its left end, as it says in the question, that we're going to call F, right? And that's going to balance this thing, because that would typically make a force, or make the thing want to rotate that way. So we have these two different forces that want to make this thing rotate in different directions. If we have the right size force, we get no rotation at all, because the net torque is 0. Okay? Now, there's a third force here, just like it asks in the question. We have to find this normal force that the fulcrum exerts on the rod. All right, those are all the forces. Okay, those are all the forces. So what we can start with, we should, just like we've done every other problem, is start with a net force statement. In this case, net force is 0 because this thing's in static equilibrium. It tells us that. All right, so what this says for sure is that, let's see, F plus mg minus n is 0. I went crazy on you. I called this way the positive direction. Okay? So notice, well, I'm just going to say this for now. How about this? F plus mg equals n. We have two unknowns, right? This one and that one. And there's no different, we can't do net force in the x direction. Where is it going to take us? There are no x forces. So with nowhere else, without where we are right now, or before this, these slides, these notes, we'd have no way to solve this problem. But now we have the idea that if this thing's in static equilibrium, it also means that the net torque is zero. So that's our second, condition we can apply. All right, so what we have to do now is we have to choose an axis of rotation, okay? And, where you put it makes a lot of difference. We have two unknowns here. So what we have to do is choose an axis of rotation that allows us to neglect the torque that one of those forces can produce. Let's say that again. We can choose an axis of rotation that allows us to neglect the torque that one of those unknown forces produces. For example, well, I will say this. In question A, we want to know what the normal force is. So what I'm going to do is I'm going to choose an axis of rotation right here. The great thing about that is if we say that's kind of like the hinge of a door, if we push with this force F right on the hinge, well, it's never going to open the door. If our axis of rotation, and again, we can choose it wherever we want. If we choose it to be there, then force F exerts or produces zero torque. Okay, so let's look at a net torque statement now. We say that net torque, I got to do this, I'm sorry. If we look at a net torque statement, equals zero, what we have to do is pick a positive. Notice, we picked a positive direction for force. We're going to pick a positive direction for torque. I'm going to say that things that go this way are positive. Torques that would make an object rotate that way around our axis are positive. All right, so now, here's where I can understand some confusion. Well, doesn't the thing rotate over that fulcrum? Well, in real life, yes. For our analysis, forget about that. And all we're talking about is imagine that we put an axis of rotation here. All right? Well, this normal force would make, if it's applied upward, would make the rod want to rotate that way, about this axis. So therefore, we call that a negative torque. So there's a torque produced by the normal force. Right? Again, our positive direction is a clockwise rotation. That normal force would make this door try to open this way. And then we have, well, the torque exerted by mg. Again, mg acts downward. That would try to make this thing rotate that way. That's our positive direction, so that's a positive torque. Those are the only torques, right? Force F, this is a real important part, a real important point. Force F here, since it acts directly at the axis, it produces no torque at all. Remember, torque is RF, well, I'll just write it as RF perpendicular. And R is the vector that goes from the axis to the place where the force acts. Well, that goes from here to here, the same place. R is zero, therefore torque is zero. All right, so dig it. This says that the torque produced by the normal force is the same as the torque produced by mg. Of course, they have to be balanced. Or this says that R for the normal force times the normal force, well, and times sine theta, right? Well, the thetas, here's R normal. There's the angle between them. Here's R mg. There's the angle between them. So those sine thetas are sines of 90, which just is 1. So I'm not even going to write it in there. So this is equals Rmg times mg. Well, we know all those R's and mg's. The only thing we don't know is n. So we can find it. So n equals R mg times mg divided by R to n. The rod's 5 meters long. So R to mg, remember, is at the center of mass. That's 2.5 meters. Mg is 12 kilograms times g, 118, divided by, let's see, R to n. Okay, well, if this is 3.5, the rest of it is 1.5. This is a 5 meter long rod, and from here over is 3.5. The rest of it is 1.5. So let's see. 118 times 2.5 divided by 1.5 is 197. So N is 197 newtons. Okay? All right. Well, now we're down to, in this case, one unknown. And we can say that F is N minus mg, or sorry, 197 minus mg. Oh, well, sorry, F is 79 newtons, right? 12 times 9.8. What do you think? Fair enough? So notice, we sort of did what we said we were going to do in the last page, right? We started with the net force statement. We ended up with more than one unknown. We came over here to a net torque statement to find one of the unknowns. We went back to the net force statement to find the other unknown. Okay? Well, that's a straightforward torque problem. Yes, good. And here's the part, where does it make sense to put it? Well, it makes sense to put it at a place, like we said before. I'll say, so I'll put this over here. We choose an AOR that eliminates torque produced by an unknown force. And where is that? Well, it's at the point of application of that force. If we say the axis is at the place where the force acts, then R is 0. R for that torque is 0, and then the torque is 0. Okay? Now, next slide, I think, yeah, let's do the same exact problem. You already know that there's a force here that, I think, what did we say it is? 79? Yeah, 79 newtons. There's a mg here, and there's a normal force here, and the normal force is 197 newtons. All right, here's your job. Pick another axis, anywhere you want. All right, anywhere other than right here. And prove to me, by writing a net torque statement, that the net torque is still 0. And what let's see, same values of F and N. Yeah, well, let's just use those known values of F and N and just prove, well, how about this? Let's say use this as an axis of rotation, right? And see that you get the same. See that you get a net torque of 0. Prove that net torque is 0 with the AOR right there. AOR, axis of rotation. All right, that's part of your job. Let's see. This is going to be the old fireman on a ladder problem. Yeah, we're going to wait. I'm going to wait till you're here on Monday to do this, because this gets tricky. Okay, so good start. Yeah, I would say also keep working on those problems, those dynamics problems. We will test dynamics and torque together on Thursday. Got that? We will test all things dynamics, all things torque on Thursday. All right, folks. All right, have a good weekend.